Welcome to Engineering Scale Models. I'm Jason, your host, and I do models. Today we're going to continue our logic series with SR latches. What is an SR latch and how does it work? Well, an SR logic is a combination logic made up of NOR gates, and there's a specific SR latch that's made up of NAND gates. But in a block diagram, you're going to have something like this. You're going to have a block, and you're going to have your S and your R, and then your Q and your Q naught. Okay, so that's your basic SR latch, and then you have an S naught, an R naught, and then you have a Q naught, and then you have your Q. So that's a not S not R latch, and then you have a SR latch with enable. This will be your S, this will be your enable, this will be your R, and you'll have a Q and you'll have a Q naught. So let's basically take a look here. Let's move this out of the way and let's look at how they work. So you have a NOR gate there. Hopefully I draw this so you guys can understand it. I am drawing not very well, I'm sorry. So here is your NOR gate, this is your R reset, and this is your set, and then coming off of here is your Q and your Q naught, and then coming off of this one it feeds back into this NOR gate, and coming to this one feeds into that NOR gate. So as you press the set button, it sets this to a high. So if you put a high here, you get a high on Q, and then you get a low on Q naught. So that's a 0. So then that would feed a low up here to this one, and if you're pressing set and this one's already low, this is going to be off, so it's going to put out a high. If this one's high and this one is low, which is high, a high and a high will get you a low. So if you look at a NOR gate truth table, you have A, B, and we'll use Q for our output. So a NOR gate, you have 0, 0, 0, 0, 1, 1, 0, 0, 0. So when nothing is inputted in there, you're going to have a 1. When this is a 1, 1. So yeah, a low is going to put out a 1. A low and a high is going to put out a... Hold on, I need to check my truth table here. I totally messed that up. I have my book of notes. I've been dealing with a lot of gates, and that one is baffling me. Why I can't seem to... Okay, so yeah, so I was going down the right path. So if any of them is high, you're going to get a 0 output because it's a NOR gate. Wow, I just kind of went away there. Sorry about that. Good thing I have notes. I have a engineering, just I log all of my notes and chips and gates and things. So you have 2 NOR gates, and this is a NOR gate truth table. Okay, and I'm going to make sure I get this right, and I'm going to flip to my notes on an SR latch, just so I have that truth table correctly. And we're going to confirm this with a circuit. So your SR latch truth table, so you have set, reset, Q, and Q naught. So there, and then you have 0, 0, 0, 1, 1 0 1 1. So if both states are at a 0, you're going to have last state. So this is going to stay whatever it was. It's going to latch the last value if none of the inputs are high. If reset is high, Q is going to be a 0 and Q naught's going to be a 1. If set is high, Q is going to be a 1 and Q naught's going to be a 0. And then if you press them both at the same time, you're going to get an unstable effect where they both go off and a random one will come on, and I'll show you that on the circuit. So you kind of don't want to feed in two highs to an SR latch. Now there are ways to prevent that with other gates, but we're going to start with the SR latch. So this is basically my horribly chicken scratched SR latch. SRLATCH. So that's my chicken scratched version of that. Let's just go to the overhead and I'll show you. I do write neater in a book. Just writing on the computer screen there is I'm still learning. So this is our SR latch right here. You get to reset your set, and then you can see they're cross connected. My truth tables for the NOR gate SR latch, and then this is an S naught R naught latch, and we'll go over that in a minute. So let's put the notes away and let's take a look at the circuit. So I am using I'll just look at my notes, a 74LS02. It is a quad input NOR gate. The inputs of this are on pin 2 and 3, and the output is on 1. It is on pin 5 and 6, output 4, and then it's the same thing on the opposite side. I didn't write that down because I'm not using that. So, and I got some meters because I want to test some characteristics of the chip. So if I turn on my power here, it is in the reset state. This is my Q, and this is my Q naught. So if I press set, the yellow is the set button, and then this is the reset. So this is my Q, and this is my Q naught. So it's reset right now. So there's nothing stored in Q. So this would be the output that I would want to store stuff with. So like I said, if I press the set button, it latches that in. So if nothing else is pressed, it's going to hold this value. Even if I press set again, it's not going to change the value. It's not going to change it until I press reset. So I can press set, I can store a value in there, I could clock it, I could do all different things with a different circuit. Say I was doing a shift register, manual shift register, and I wanted to input 1s and 0s. I could hook up the serial data line to the shift register, and when I want a 1, I could press the set button, and when I want a 0, I could press the reset button. So there's set, reset, and you can also look at it like, let's take out Q naught. So now you just have the regular storage register. You can store data, and then you can clear the data. You can store a 1, and you can clear a 1. And imagine if you had, 8 of these hooked up, 4 chips. You'll get 2 out of each chip because they're NOR gates. You can get SR latch chips that have 4 on it, but you could have 2 latches per chip, and you had 2 chips. You could have 4. You could have 4 bits of data, and then you could plug in numbers and do different things with those numbers if you wanted to make something out of simple logic. So I'm going to put this back in because I want to do an experiment here. So I'm going to turn the circuit up, and I'm going to hook up these 2 meters here. These are my cheapy meters I measure amperage with, and I want to show you what kind of low amperage that this circuit draws, the chip itself, and we're going to use Q naught because I have it set up for that. So let's turn off the circuit and let us pull out this lead here and hook this up like this. So we got positive flowing through the amp meter, I'm going to go to 20 milliamps, and then I'm going to take this one and I'm going to pull out my power jumper, which I made jumpers so you guys could see the colors. And then I'm going to plug in this meter, red to positive, black to the chip. I'm going to set that to 20 milliamps. And then I am going to turn this to DC voltage so we could just probe around and see what the voltages are. Can you see that? I found that this meter shows up better than that meter right there. That meter, if I turn this meter on, I mean, it shows up, but the Lumia one I can have next to the board and it shows up better. So we're going to use this one. I don't care for it. It's a higher end meter, but it just acts weird. So we're going to use that to measure the voltage across some stuff like the resistor and stuff like that. So I'm going to turn on the circuit. It's going to start with in the reset position, and as you can see, the chip itself is drawing 7.5 milliamps, lighting this LED, and the LED is drawing 7.42. So if you subtract the two, because the chip is driving the LED, really 0.05 milliamps is what the chip is using. The chip is using only 0.05 milliamps itself, the quiescent current of the chip. So if I switch this, let's switch that, and the current through the chip jumps up a little bit from 7 milliamps, but that could be just a different voltage drop across the LED. So let us measure the current in that one also. So I am going to turn this off for a second. I'm going to close this. I'm going to plug Q0 back in. Unplug Q. This is nothing to do, just to swap it around. So if I set it, it drew 10 milliamps there for a second. I could put this on the scope to see the curve, but 7.9, and with this LED it's about 8.08 milliamps difference. So, and it could be a different forward voltage on these LEDs. Let's check that out. So this one is drawing a forward voltage of 2.88, and if we reset it, what is this one drawing? So 2.89, they have about the same forward voltage. What's the drop across the resistor? Resistor's dropping 1.68. I would expect the resistance to drop the same, 1.68. 1.7. So, and if you did the math, you would get the 7.8 milliamps. The voltage out of the output referenced to its own ground is, what output am I using? Output 1. So if I check the voltage on the output, I'm getting about 4.68 volts going to the output. So, and then the voltage on the chip is 4.89, and that was 0.68. So about 2 millivolts or 100 millivolts is being used by the chip, is the voltage drop across the chip, the difference there. So our 0.1 volt, so about 0.1 volt difference that the voltage of the chip is doing. So that is about it for this SR latch. We're going to look at the S0 R0 latch next, and that's made with NAND gates. So I'm going to pause and I'm going to get that set up, and then we are going to take a look at that and we're going to see if that chip draws any kind of different amount of current, and then we're going to go back to this chip with an enable line. Okay, now we're going to look at the S0 R0 latch. There's the block diagram for it. It is made with NAND gates, so we'll write NAND gates, NAND, and we'll write the truth table for a NAND gate. And we'll use Q for the output. So 0, 0, 0, 1, 1, 0, 1. They're both 0, it's a 1. And then this is a they both have to be 1 to be a 0. So it's a 1, 1, 1, 0. So they both have to be 1 to be 0. So it's not AND. So it's just like an AND gate, but it's the opposite. Now, the not S, not R latch is similar to the SR latch, but it uses NAND gates, which hopefully I draw a little better than the NOR gates. So we got R, S, R naught, S naught. There's our outputs. There's Q and Q naught. Now the difference with using this gate is with the standard SR latch, I pulled the inputs low. So these need to be pulled high. So these need pull up resistors. So pull up resistors. So let's show you that in implementation, and then we'll look at how it works with the truth table there. So we come back to our chip. Here is our chip. It is a 74LS00. It is a quad 2-input NAND gate. If we turn on the circuit, it is in the set position. If I press the reset button, it will reset. If I press the set button, it will set. So it is almost similar, but I had to use a pull-up resistor and connect the LED to ground, so I had to reverse the switch order. But that is that. Let's check the current draw of the chip, because I want to see if it's different from the last chip, which was about 0.05 milliamps, and then we will get this out of here, and we will check it to subtract the amperage. So I'll go to 20 milliamps, 20 milliamps. So you can see the meter. So this is the chip and this is the LED. We will turn on the circuit, we will press the, and now it doesn't want to work. That's because, nope, that's right. So why is that acting weird? If I just plug that back in. I must have messed something up. Power. It's drawing about 8 milliamps, but it's not giving me an output of. I wonder if it just doesn't like the meter in line with it. Yeah, it just didn't like that meter. Weird, it didn't like the resistance of the meter. That was strange. Guess the voltage drop in the meter to measure the current was too much for it. That is strange. Let's see if we can measure the current now. So we're getting about 7.2 milliamps onto the LED. That is strange why I can't measure the current of the actual chip. That is a strange one. But anyways, that is the SR latch made with NAND gates. Now we're going to look at an SR latch with enable. So, oh, hold on, let's check the voltage of the chip. Let's see what the voltage is across the chip. It's getting 4.97 volts. Let's check. You know what? I want to see what the voltage drop across the chip is with that meter in line with it. So, again, it won't work. And it's drawing 8 milliamps just to do that. What is the voltage drop across this chip? It's 4.87 volts, so it's within its tolerance. What is the voltage drop in reference to ground across this output here? 4.5. If I look at this output, wow, if I press the reset button, oh, see, now it's working. Okay, sorry about that. So if I measure the voltage from ground to this output here, it works. But if I pull that voltmeter out, it won't work. So we're going to put it back in and we're going to measure the current and see what the quiescent current is. So it is 9 milliamps. So let's put it back on here. So 8.6, 8.7, and 6.9 on the LED. So it's drawing a good milliamp. That's strange. If I swap it, it's drawing about 9. And then boom, it jumps up to 17 milliamps just to switch the LED. Now it's not switching them again. That is strange. That is strange, strange, strange. I am not that versed in electrical engineering to be able to tell you why it didn't like those meters. They are crappy, cheap meters, so now it works. So they are crap, cheap meters. Maybe they put too much resistance in line or whatever. But next we're going to look at the SR latch with the NOR gates with the enable line. So I'm going to get that set up. Okay guys, the last one we're going to look at is the SR latch with enable. So let's scooch over here. So this one has 3 inputs and 2 outputs. It has your Q and your Q not. It has your set, reset, but it has an enable. And how this would work is you have your standard NOR gate situation here, like this, and then this goes out. This is your Q, and this is your Q not, and then this one goes up here, and this one jumps over that and goes into there. And then, you know, normally you would have your set and reset, but they come into AND gates, and then now you have down here, you have your reset and your set, and connected to these 2 gates you have your enable. So these are and these are NOR. I can't write that in there. So it's the same as your SR latch, but it only works when you press the enable button. So, and then we'll modify this in later videos on different types of latches that use this base system. So let's take a look at the circuit here. So I have my set, set, reset, and enable is the red button, is the new button on here now. And then we have our Q and our Q not. So we turn our circuit on, it is in the set position. Let's reset. Oh, yeah. So if I press the set or reset, nothing happens. I have to press the enable, and then I can reset it, and I can set it, reset, set. But if that's enables not, no matter what comes through on the set and reset lines, nothing happens until that enable is pressed, and then I can do something. So, and it's still, if you press both of them, it still errors out. But if you press both of them when the enable's not enabled, it works out. So if you want to clock data this way with an enable, you can make sure you have your right one done before you push the enable, so you can have that on. So you press your set, and then you press the enable, you press your reset, and then pop the enable, set, pop the enable. So you can have your S or R high, and then have a pulse come in and set it, and then everything can go low, and then you could set up for another input. I'm curious. Well, we already checked the current of these chips. I'm not going to waste time checking the current of these chips. But that's going to do it for the SR latch series. We covered the 3 latches. I hope it was informative and you guys learned something. You can visit me on social media, leave me a message, leave me a comment. You can also support me on Patreon. I'm trying to save up for some new test equipment to get some new projects and to get some work done. So if you could support me on there, that'd be greatly appreciated. But that's going to do it for this video. Thank you so much for watching.